asked, how good is the test at identifying people with the disease and people without the disease? This is an important issue, particularly in screening-free living populations. In effect, we are asking, if we screen a population, what proportion of people who have the disease will be correctly identified? This is clearly an important public health consideration. In the clinical setting, however, a different question may be important for the physician. If the test results are positive in this patient, what is the probability that this patient has the disease? This is called the positive predictive value (PPV) of the test. In other words, what proportion of patients who test positive actually have the disease in question? To calculate the positive predictive value, we divide the number of true positives by the total number who tested positive true positives plus false positives. Let us return to the example shown in Table 1, in which a population of 1,000 persons is screened. As seen in Table 7, a 2 times 2 table shows the results of a dichotomous screening test in that population. Of the 1,000 subjects, 180 have a positive test result. Of these 180 subjects, 80 have the disease. Therefore, the positive predictive value is 80/180ths, or 44%. A parallel question can be asked about negative test results. If the test result is negative, what is the probability that this patient does not have the disease? This is called the negative predictive value (NPV) of the test. It is calculated by dividing the number of true negatives by all those who tested negative true negatives plus false negatives. Looking again at the example in Table 7, 820 people have a negative test result, and of these, 800 do not have the disease. Thus, the negative predictive value is 800/820ths, or 98%. The relationship between predictive value and disease prevalence can be seen in the example given in Table 8. First, let us direct our attention to the upper part of the table. Assume that we are using a test with a sensitivity of 99% and a specificity of 95% in a population of 10,000 people in which the disease prevalence is 1%. Because the prevalence is 1%, 100 of the 10,000 persons have the disease and 9,900 do not. With a sensitivity of 99%, the test correctly identifies 99 of the 100 people who have the disease. With a specificity of 95%, the test correctly identifies as negative 9,405 of the 9,900 people who do not have the disease. Thus, in this population with a 1% prevalence, 594 people are identified as positive by the test, 99 plus 495. However, of these 594 people, 495, 83%, are false positives, and the positive predictive value is therefore 99/594ths, or only 17%. Let us now apply the same test with the same sensitivity and specificity to a population with a higher disease prevalence, 5%, as seen in the lower part of Table 8. Using calculations similar to those used in the upper part of the table, the positive predictive value is now 51%. Thus, the higher prevalence in the screened population has led to a marked increase in the positive predictive value using the same test. In the discussion that follows, the term predictive value is used to denote the positive predictive value of the test. A second factor that affects the predictive value of a test is the specificity of the test. Examples of this are shown first in graphical form and then in tabular form. Figure 10a diagrams the results of screening a population. However, the 2 times 2 tables in these figures differ from those shown in earlier figures. Each cell is drawn with its size proportional to the population it represents. In each figure, the cells that represent persons who tested positive are shaded blue. These are the cells that will be used in calculating the positive predictive value. Figure 10a presents the baseline screened population that is used in our discussion. A population of 1,000 people in whom the prevalence is 50%, thus 500 people have the disease and 500 do not. In analyzing this figure, we also assume that the screening test that was used has a sensitivity of 50% and a specificity of 50%. Because 500 people tested positive and 250 of these have the disease, the predictive value is 255/100ths, or 50%. Fortunately, the prevalence of most diseases is much lower than 50%. We are generally dealing with relatively infrequent diseases. Therefore, Figure 10b assumes a lower prevalence of 20%, although even this would be an unusually high prevalence for most diseases. Both the sensitivity and the specificity remain at 50%. Now only 200 of the 1,000 people have the disease, and the vertical line separating diseased from non-diseased persons is shifted to the left. The predictive value is now calculated as 100/500ths or 20%. Given that we are screening a population with a lower prevalence rate, can we improve the predictive value? What would be the effect on predictive value if we increased the sensitivity of the test? Figure 10C shows the results when we leave the prevalence at 20% and the specificity at 50%, but increase the sensitivity to 90%. The predictive value is now 180/580ths or 31%, a modest increase. What if, instead of increasing the sensitivity of the test, we increase its specificity? Figure 10D shows the results when prevalence remains 20% and sensitivity remains 50%, but specificity is increased to 90%. The predictive value is now 100/180ths or 56%. Thus, an increase in specificity resulted in a much greater increase in predictive value than did the same increase in sensitivity. Why does specificity have a greater effect than sensitivity on predictive value? The answer becomes clear by examining these figures. Because we are dealing with infrequent diseases, most of the population falls to the right of the vertical line. Consequently, any change to the right of the vertical line affects a greater number of people than would a comparable change to the left of the line. Thus, a change in specificity has a greater effect on predictive value than does a comparable change in sensitivity. If we were dealing with a high prevalence disease, the situation would be different. The effect of changes in specificity on predictive value is also seen in Table 9. As seen in this example, even with 100% sensitivity, a change in specificity from 70% to 95% has a dramatic effect on the positive predictive value. This is our course about screening and early detection. Thank you for your listening.